A common myth in system design suggests that making every process asynchronous is the only way to achieve high performance. The logic is simple. If the server never makes the user wait, the app will feel fast. In practice, optimizing exclusively for raw speed creates a broken user experience. When every action is pushed to the background, users encounter a ghosting effect. They see a success message, but their data hasn't actually updated yet, leading to confusion and a loss of trust. The opposite extreme is just as damaging. A fully synchronous system forces the user to wait behind a loading spinner for every minor background task, effectively freezing the interface until the database completes its entire checklist. Architects resolve this tension by choosing between the delivery of momentum and the delivery of certainty. Performance depends on the intelligent management of wait times. The goal is to identify which operations require the user's attention to maintain data integrity and which can be safely hidden. Synchronous processing operates as a sequential lock. The system prevents the user from proceeding until a specific task is finished and verified. This diagram shows the request moving through application layers. The blocking mechanism prevents the server from returning a signal until the database execution is complete. This is required for payment gateways. The user waits while the system confirms funds before safely allowing the next action. Processing a payment asynchronously would create systemic chaos. If an app reports a successful purchase before the bank actually clears the charge, the user might find their order canceled 10 minutes later when the background task finally fails. For critical financial or security operations, blocking the user is a functional feature. It guarantees that the state of the system is accurate before the user moves forward. Asynchronous processing takes the opposite approach, decoupling the user's action from the system's heavy lifting. This network diagram shows a request hitting the server, instantly looping a success signal back. Simultaneously, the server drops a data packet into a holding queue. Autonomous worker processes pull tasks from this queue, executing work in the background, entirely disconnected from the active user. When you upload a video, the system saves the file synchronously, so it isn't lost. But it generates thumbnails, sends notification emails, and updates analytics in the background. This architecture protects the user's momentum by shifting high-friction, non-essential work into the shadows. Developers need a systematic way to choose between these two paths. The decision determines how the system will scale and how the user will perceive its speed. This decision tree asks, does the user immediately need the result to proceed? If no, use the asynchronous path. Dispatching an email or logging analytics can wait in the queue. If yes, inventory validation and core database writes require immediate confirmation, making the operation synchronous. Choosing the asynchronous path introduces eventual consistency. This means accepting that for a brief window, different parts of the system, like a follower count or a dashboard, might show slightly outdated data until the background workers catch up. Scalability relies on minimizing the amount of work performed during the active request. By separating immediate requirements from background tasks, developers can maintain system integrity without sacrificing the speed of the interface.